7.4 Evaluate logarithms and graph logarithmic functions. Today we're going to be learning about logarithms. You won't really understand this comic until we get to the end of this lesson, but it goes like this. Oh, I just fell and I'm seeing e's. Here, I've got something that'll help, natural log. So we've been learning about e's in our previous lessons, and today we're going to learn about natural log, ln. Logarithms give us the answer to the question, how should we solve 2 to the x power equals 6? We learned about inverse functions in the previous chapter, and so we're going to apply that idea, and we're going to learn about logarithms. And logarithms, what they do is they undo the exponential. So in order to undo 2 to the x power, we could take the logarithm of both sides of this equation. Since we have a 2 in the base, we're going to take the log base 2 of each side. And since they're inverse operations, we just get x left. So x equals log base 2 of 6. Now I'm going to explain this over and over again throughout the lesson, but solving this equation just means 2 to the what power equals 6. That's how logarithms work. So let's take a look. The definition of a logarithm with base b is just that log base b of y equals x is equivalent to the statement b to the x power equals y. That, in a nutshell, is what we're going to be talking about. So log base b of y equals x is equivalent to the statement b to the x power equals y. And we read log base b of y as log base b of y. I think this will make things make a lot more sense. Because 2 to the 5th power equals 32, we know that log base 2 of 32 equals 5. So basically here is always your base. This is your base. This would be the exponent you're raising it to, equivalent to this. And then here's kind of just your answer part, which is equivalent to that. Since 10 to the 0 power equals 1, I can say log base 10 of 1 equals 0. 9 to the 1st power equals 9. 1/5 to the what power equals 25. So that's what I'm asking you. 1/5 to the what power equals 25. Well, we know we want to flip that because we know that 5 to the 2nd power is equal to 25. So since we needed to flip it, that's just the negative. So that's why log base 1/5 of 25 equals -2. Okay, let's do some without the answers written. 3 to the what power is 81? That would just be 4. 1/4 to the what power is 256. So first, let's say we know that 4 to the 4th power is 256. So that means that since we have 1/4, we would do it to the -4 power to get 256. Let's see. This is saying 10 to the what power is 0.001. So since I'm moving the decimal over 1, 2, 3 places, that would just be -3 power. -3. And you can think back to scientific notation to kind of get that answer, or you could put it as a fraction. Lots of ways to do that problem. 64 to the what power is equal to 2. Now, obviously, the number is getting smaller, so we're actually taking a root. So this is going to be a fractional something, and you might not know. So let's just break 64 down. 64 is 32 times 2, which is 8 times 4 times 2. So 8 is just 2 times 2 times 2, and then 4 is 2 times 2, and then bring down the 2. So we have 1, 2, 3, 4, 5, 6. 2 to the 6th power is equal to 64. So 64 to the 1/6 would be equal to 2. So our answer is just 1/6. Now the common logarithm, when we just write log, that automatically means log base 10. So just like when you see the square root, you know that the 2 is automatically on top of the radical sign. If you don't see anything written here, then it's automatically log base 10. And so the log key on your calculator is automatically log base 10. So the common logarithm is just a log with base 10. And obviously we abbreviate logarithm with log. Now the natural logarithm, we abbreviate ln, and that's log with base e. So ln of x, for instance, is equivalent to log base e of x. Let me just put x's here because log is a function. So I'm going to explain that better in the examples coming up, but here's a little comic again. Log says, people have 10 fingers and 10 toes. It makes sense to use base 10. And ln says, naturally. Ha ha ha. So when we use a calculator to evaluate these things, we're really just going to use the log key and the ln key. Not very difficult. Your log key is right here, and your ln key is right below it. So if I want to do log of 0.85, I just type it in like that. That's my answer. If I want to do ln of 22, I type it in like that. And that's my answer. The sales of a certain video game can be modeled by y equals 20 ln x minus 1 plus 35, where y is the monthly number of games sold in thousands, and x represents the number of months since the release of the game. Estimate the number of video games sold during the 10th month after the game is released. And so x is the number of months since the game has been released. So the 10th month after will be when x equals 10. And so we know that y is going to be equal to 20 ln 10 minus 1 plus 35. And we can use our calculator to do this. 20 ln 9 plus 35. So we'll do 20 times ln 9, parenthesis, plus 35. And so we get y is approximately equal to 79. But make sure we go back and read our problem. Y is the monthly number of games sold in thousands. So how many do we sell? We sell about 79,000 games. And it's very important that you go back and you look for units there and that you note that it's in thousands. I said here, note the importance of the restriction on the domain. We do have to restrict the domain to x is greater than 1 here, and that is because we can only take the ln of a positive number. And I'm going to emphasize that when we look at the graph coming up. So basically, the very important part that I've tried to explain here, and if you go back and look at the comic after this, it'll make a lot of sense. The logarithm and exponential functions are inverses of one another. And I want to prove that right now. So basically, I want to show that, let's say, b to the x power. Okay, I want to show that the exponential and the logarithmic, that would be log base b of x, I want to show that they are inverses of one another. So f of g of x in this case is going to say do f to log base b of x. Do f to it. So do b to the log base b of x. They are inverses. They undo one another. And so we just get x back out. G of f of x says do g to b to the x power. So when you take the log base b of b to the x power, you just get x back out. I do need to have the same bases here for the operations to undo one another. So when I say 10 equals log of 4, remember if there's no base written, it's always a 10. And since the bases are the same of both of those operations, we just get 4 because they undo one another. Now here, they're not the same. But isn't 25 the same thing as 5 squared? I think so. So we could say log base 5 of 5 squared to the x power. And we know that a power to a power just means multiply. So 2 times x is 2x. And now that we have log base 5 of 5 to the 2x, those operations undo one another, and we just get 2x as our answer. So I bet you know what the inverse of 6 to the x power is, since we said that log undoes the exponent, but let's just prove it. Let's switch the x's and y's, and now to get the y by itself, to undo the 6 in the base, I must take the log base 6 of both sides. And so I have x there and 6 to the y there. And so log base 6 of 6 to the y is just y itself, because they're inverses. And so I get log base 6 of x. So the inverse operation is just y equals log base 6 of x. Let's do the same thing over here. X equals ln y plus 3. What undid an ln? Remember, ln of x is just log base e of x. So to undo an ln, you just need an e. So both sides, if you do e to that and e to this, since the e and the ln undo one another, we are just left with y plus 3 over here equals e to the x power. Subtract 3 from both sides, y equals e to the x minus 3. And that is our inverse. Now let's just look at the graphs. Obviously, since they're inverse functions, we just reflect it over the line y equals x. So this would be the line y equals x. We know very well right now what y equals b to the x power looks like. It was exponential growth. And so when we reflect it over, this point that we said was very important, that 0, 1, just becomes 1, 0. Why does it become 1, 0 anyway? Well, log base b of 1, that says b to the what power is 1? B to the 0 power is 1. Because b to the 0 power equals 1, that's why we know that the point 1, 0 holds. Now when looking at the domain and range, let's start with what we were doing before, which was y equals b to the x power, the blue one. And we knew that our asymptote was at y equals 0. Y equals 0. We saw that our domain, it took in all real numbers, and our range only popped out y values greater than 0. So now when we look at the log base b of x, where b is greater than 1, which is the red function here, we just flip all the x and y stuff. The domain of log is just the same thing as what the range of the exponential was. So the domain would be x is greater than 0. So you look at this. The range would be all real numbers. Kind of flip the x and y stuff, right? And then the asymptote, instead of y equals 0, will just be x equals 0. And let's look at our red graph. The asymptote is at x equals 0. The x values it can take in are just the positives. And the range, well, it pops out all real numbers. And so you'll see that all of our properties, the x and y stuff has just been interchanged because, again, the definition of inverse functions is that you just swap all the x and y stuff. It's a reflection over y equals x. Let's think through the same process when we're doing b to the x, and now our b is some number between 0 and 1. Well, we knew that our properties there were that the domain, again, was all real numbers, the range was y greater than 0, and the asymptote y equals 0. It was the same properties as it was in this function here, except instead of having exponential growth, we had exponential decay. Now we're going to be looking at log base b of x, where the b is between 0 and 1, and the red graph is just a reflection over the y equals x of this blue graph. Now it looks a little bit different than it did in this one just because the way the function originally looked. But we'll do the same thing over here, and we'll swap all the x and y stuff. The domain will just be x is greater than 0, so it only takes in positive values. The range is now going to be all real numbers, and the asymptote, instead of being y equals 0, is just going to be x equals 0. So again, I just swapped all the x and y stuff. So now let's do some graphing ourselves. Honestly, I just think of the inverse function when I'm graphing these and switch all the x's and the y's. So I think about y equals 2 to the x power, because that would have been the inverse. So I'm going to first make a table of values for 2 to the x, and then I'm going to show you what I just think of when I do this every day. So we have xy, and I'm just doing y equals 2 to the x power right now. Let's just use -1, 0, 1, and 2. So 2 to the -1 is just 1/2. 2 to the 0 is 1. 2 to the 1 is 2. 2 squared is 4. So when I go to make a table of values for the inverse, I just literally swap all the x's and y's. So when I have y equals log base 2 of x, I literally just go -1, 0, 1, 2, and then 1/2, 1, 2, and 4. And that's how I graph it. So we have 1/2, -1, 1, 0, 2, 1, and then 1, 2, 3, 4, 2. Keep in mind that your asymptote is here. That's important. And then your graph's going to go like this. In this function here, you bet I'm going to think y equals 2/3 to the x power to make my table. So when I make my table, I don't usually write both of them. So this will be the table for y equals log base 2/3 of x. I just usually start with my y values, so -1, 0, 1, 2, and then I think to myself, 2/3 to the -1 is just 3/2. 2/3 to the 0 power is 1. 2/3 to the first power is 2/3, and then 2/3 squared is 4/9. So I just kind of flipped it all in one step. Nothing fancy. So graph that 1.5, -1, 1, 0, 2/3, 1, and then 4/9, 2. Nothing has shifted at all here, so our asymptote would still be at x equals 0, and it's going to look something like this. Remember that this equation would have been decay, so it makes sense that our graph looks like this in that case. Our last example is going to, of course, be a transformation. So I'm just going to start with the parent function, which would be y equals log base 3 of x, and then I'm going to apply my transformation. So to make my table of values for this, I'm going to be thinking that my inverse is y equals 3 to the x power. So give yourself some space here because we're going to do a transformation to it. Let's start with the y values, -1, 0, 1, and 2. And so we do 3 to the -1 is 1/3, 3 to the 0 is 1, 3 to the first is 3, and then 3 squared is 9. So there is no stretch here, so let's shift it 2 units right. So we have 2 1/3, 3, 5, 9 plus 2 is 11. And then 4 units up. So we have 3, 4, 5, 6. So go ahead and plot these. I can't fit 11/6, so I'm not going to. Now where is my asymptote? My asymptote used to be at x equals 0, but now we're moving it 2 units right. And the reason I knew to look at the x stuff was because my asymptote was at x equals 0, signaling me to look at x stuff. So my asymptote is going to be at x equals 2 now, here. And so my domain, it used to be x is greater than 0, but now I've shifted everything 2 units. So I just have x is greater than 2. My range was all real numbers. So even though I shift it 4 units up, it's not going to change from all real numbers, right? And so that is my graph. I just have to keep in mind the asymptote there. The asymptote's very important in drawing your graph. So just in sum, what I did was I started with the parent function, log base 3 of x, then I applied my transformations, shifted 2 units right and 4 units up, so 2 units right, 4 units up, and then to think about my asymptote, well, I knew that my asymptote was at x equals 0, but I thought about what happened to x in this problem. So I looked at what happened to x. It shifted 2 units right. So that's why I got x equals 0 plus 2, or 2. When I thought about my domain, it used to be x is greater than 0, but now I shifted it 2 units right, so I have to add 2 to it. X is greater than 2 will be my domain. My range used to be all real numbers. Even though I shifted all the y stuff up 4 units, well, I'm still going to cover all real numbers. And that's it for this lesson.